So in this slide, which everybody has access to, and I encourage you to look at the slides. I'm just going through them. So somebody showing a chart. This pie chart shows how much pie I ate while making this chart. Is this data or not data? Anybody? Why not, John? Why is that not data? Okay, I'm going to tell everybody, don't guess if you're going to answer a question, because you have to have some kind of rationale for your explanation. That is also part of statistics. Anybody else? Okay. Remember what I said in the first class? There are no numbers? No. Data doesn't have to have numbers. Okay, so if obviously I'm saying this is data. Don't worry about it, John. The data is, this is personal data. He's saying I ate pie while making the chart. Even though it doesn't make any sense, it is data. It's information. It's basically irrelevant information, but it's information. And remember how I mentioned on Tuesday how data is information, whether it's relevant data, irrelevant data, bad data, or good data. So just remember that when you're looking at information and looking at it for your personal study, the case study. Okay? Whoop. Okay, so these are the learning objectives for the class. Know the key data collection methods. Know the difference between a population and a sample. A sample is a small subset of the population. The population is everybody or everything within that set. So if you're going to study flowers, you take a subset of the flowers. But if you're going to study flowers, you have to use every single flower. Number 3, understand the similarities and differences between different sampling methods. Understand how to categorize data by type and level of measurement, and become familiar with the concept of data mining and some of its applications. So I just want to mention that I don't know if everybody has this, but my internet is very slow. So excuse me if the slides don't go along smoothly. Okay, so why study statistics? Now what I'm going to do is I'm going to get the video and try to show it to you. So just give me about a minute or two. Very slow. Tried this the other day and it worked fine. And it doesn't seem to be working fine now. Sorry, everyone. Internet is extremely slow.
So in high school, I had never even heard of statistics. And I knew I liked math and I knew I liked science.
In high school, I went to a conservatory for music. I was a viola performance major.
When I started college, I was taking a bunch of math and economics classes. And then in my junior year, I took a probability and statistics class.
I remember sitting there in the classroom thinking, wow, this is a really interesting problem. And he's using statistics and probability theory to try to solve it.
Statistics is amazing because it has many diverse applications, from search results on Google or Bing to recommendations on what you should be shopping for on Amazon.
If you're watching a YouTube video and at the end you get recommendations for other videos, statistics were used to give you those recommendations.
I've seen statistics in ice skating. I've seen statistics in agriculture. I mean, I've seen statistics in climate control. I mean, statistics can actually be anything that you like, anything that you enjoy, anything that you want to do, anything that you're passionate about. You can, take statistics and it fits.
I'm very lucky to get to use statistics to answer some of the questions that I think are the most important questions about social justice and human rights violations. And on my best days, I get to spend the majority of my day doing data analysis to answer questions for the United Nations, to contribute evidence to war crimes trials.
As a part of my PhD, I created a statistical software package, and Google emails me every time someone uses it. And people have used it to analyze DNA and find genes that are related to cancer.
It's even used in the food pyramid. You know what I mean? When we come up with suggestions, of what you should eat and how much of it you should eat, we try those things using statistics.
Statistics is critical for everybody entering the workforce because so much of industry and government and everything today is data driven.
Just like it's important that we all know how to read, we all need to know statistics.
Look around you. Everywhere you are, there's data, there's information.
Whatever your passions are, statistics will be involved.
We're producing so much data these days. Regardless of the field that you pursue, whether it is astronomy, criminal justice, and medicine, going forward, you've got to know statistics.
So did everybody get to watch the video? I hope. Okay, great. Did it inspire everybody? Now you all want to go into statistics? You got to pronounce it properly. Okay. Oh my God. You don't know about that. Why not? Sorry, I'm trying to get the PowerPoint back up. It's rather slow. Okay, sorry, some questions here. All right. Oh, and why would you just want to use the info if you didn't know where it came from? That's a question from Ocean. How do you know that it was valid information, Ocean?
Well, I would be hoping that I could trust the person giving it.
No, you cannot. The one, okay, I'm going to go through this eventually, but the one thing, there's more than one thing, which is extremely, it's basically what I mentioned the other day about garbage in and garbage out.
Mm-hmm.
Unless you know your source is 100% reliable, the data is not reliable because you don't know how they collected that information.
Mm-hmm.
Has anybody in the class studied psychology? Anybody?
I did criminal psychology.
Okay. You probably wouldn't know this one. In the 1920s, there was a very famous psychologist, Cyril Burt, who
Mhm.
studied children, the development of children, right?
Oh, yes, yes.
Okay.
Yeah.
He had many articles published and said he had tested over 1,000 children. Well, guess what? 20 years after that, that's how long it took. They found out that he made up all the data. He never
Oh.
tested 1,000 children. He may have tested 5 or 10. He didn't have access to them. So he made up the data and looked good enough that everybody believed what he had done, but nobody replicated what he did. And that's the important things about doing research and doing statistics. Because when somebody finally tried to replicate what he had done, guess
Mhm.
what? None of it worked. So he made it all up.
That's crazy.
Yeah, that's crazy, but it happens. So you must
Yeah.
trust your sources of data. So just going on. So statistics is also, by definition, an information science and use both computing power and new computing environments that drive much of the current research. So an interest in computation and or computer science can also be a start for a statistician. I'm going to mention this. I don't know whether we're going to have time in class. I did mention Apps Anywhere, which is available to all GBC students. On the app, there is something for SPSS and something for SAS, SAS. If you are interested in trying to use some software, maybe offline, you can send me an email and I can get you started on using the software. And what instruments are we going to be using in this course? You're going to use your calculator and Excel. But as I said, when you are going for a job interview, it's always better to have a backup and say, hey, I know how to use this software, which will certainly impress the future employers. And software, that's the software we're using. That's all. Okay, so one advantage of working in stats is that you can combine your interest with almost any other field in science, technology, or business. Statisticians are employed in many industries, including biology, finance, economics, engineering, medicine, public health, psychology, marketing, education, and sports. In all of these areas and many others, statisticians work closely with other scientists and researchers to develop new statistical techniques, adapt existing techniques, design experiments, and direct analysis of surveys and retrospective studies. So depending on what you want to do, and I mentioned the majority of people in the class are in accounting. As somebody who might be a forensic accountant, you would be called on, and there's not very many people because for whatever reason it's statistics and you may not remember it, to investigate companies. You could work for the government. So don't put out, there's always a possibility. So I'm not going to play the video because it just took too long. You can look at it at your leisure. So statistics is the science of gathering, analyzing, interpreting, and presenting data. And that is referred to as a research methodology. How do you get the data? Where does the data come from? What do you do with the data? How do you analyze the data? And what conclusions can you draw from the data? So it's a bunch of mathematics, but it's not mathematics. It's a course of study. It involves facts and figures. A death is a statistic. Measurements that are taken on a sample, and the type of distribution being used to analyze the data. I think everybody's done the introductory math, and gathering from the last class, everybody did a little bit with the measures of central tendency. Am I correct or not correct? Anybody? Did you do like the mean, the mode, and the median? Okay, so you have some basic understanding of that. And I'm going to tell you right now, in statistics, and not, you don't want to get into complicated statistics, but basically what statistics is the measurement of the means of different populations or different samples. And you want to see if there is a statistical difference between the two. And that's what statistics basically comes out to. So it's not that complicated. The applications might be complicated and the analysis might be complicated, but the results are basically the same. You want to tell the differences between two different groups, whether it's a sample or whether it's a population. Okay, and specifically, this is where you can find statistics in business, and you may have already taken some courses. Everybody has taken economics, I think. I think you had to take that in the first semester. Yep, okay. Micro, and some have done macro. So you use statistics there, and you're looking at different graphs, basically about supply and demand, and you're looking how they affect each other by looking at the graphical representation of that data. So the main objective of business statistics is to make inferences about certain characteristics of a population in the business domain, whether the population is people, objects, or collections of information. Remember, it's all data. So you may do a survey, and you may see males have a preference for a certain type of shoe or something. You're working at a marketing company. So you are focused on those males because your pilot study, or what's referred to as a beta study, maybe you tested 20 people, 30 people, and this information came out. It's a characteristic. It was statistically significant. So you might make your marketing campaign based on that study that you did. A population is the entire set of data, and any real-life sample is normally only a subset of the data contained in the population. So if you think about the Canada census, that is a census of the population. It's everybody in the country of Canada. Everybody is taken account of, whether they're children, whether they're adults, whether they're your grandparents, everybody is counted. That is an entire set of data. And that's how important the census is in Canada, because decisions are made about pensions, about subsidies, other things that affect the population. That is probably the best data set. I've worked on that data set, not for a long time, but I want to tell you that obviously there are millions of observations, and there's thousands of different variables that you can measure. So you can find lots of information there and make lots of inferences from the data, which affect the change. And that's why you use statistics to see if you're going to affect a change. You're going to change some condition. And what's important when you take a sample, which again is a subset of the total population, you want it to be random, because randomness is essential to make sure the sample is representative of the population when it is used to make predictions or decisions about the population. And therefore, business statistics is the science of intelligent decision-making in the face of uncertainty, and is used in many disciplines such as financial analysis, econometrics, auditing, production and operations, and marketing research. So remember, if you have a question, just put up your hand and we'll try to answer that. And the subject of business statistics typically covers statistical study, descriptive statistics, which is a collection, description, analysis, and summary of data, probability, which is the easiest thing to know about that is when people roll dice, what's the probability of getting an 8, the probability of getting a 12, whatever. and data distributions, a test of hypotheses and confidence intervals, linear regression, and correlation. Statistics is a science of making decisions with respect to characteristics of a group of persons or objects on the basis of numerical information obtained from a randomly selected sample. And a random sample is only a sample of a finite number of outcomes of a random process, and one cannot normally see a random sample. You can't go out on the street and, start picking people and say, oh, they're all from the same kind of group. So at the planning stage of a statistical investigation, the question of sample size is critical because a larger sample provides more relevant information and as a result, a more accurate estimation and better statistical judgment regarding the test of hypotheses. So if I want to do a study, if I want to do a marketing campaign, is it better to test 10 people or 100 people? Anybody? Why? Okay, tell me why. Does anybody know why it's better to test more people than less people? It's more indicative of the answer. It's more data. You're all around it. More valid. Yeah. Why is it more valid, Brenda? Can you think of why it's more valid?
Because I think answers are coming from a lot of people, different opinions, different backgrounds, different demographics.
Right. Okay. Everybody's around this. Basically, what happens is the more people or the more data points you can gather, it's closer and more representative of the population. So if your population and everybody can't, survey everybody in the city of Toronto, you take a representative, but you take a big enough sample that you think it's representative of the population. Does everybody understand that? The closer, the higher number that you have for a sample, the closer you get to what the normal population looks like. Is that clear? Okay. So you normally resort to looking at a sample chosen from a population and trying to infer information about the entire population by only examining the smaller sample. And let's cut off at the bottom. The two important numbers of the population are the mean, which is an X with a bar over it, and the standard deviation, and that is the Greek symbol for sigma. So, business statistics provide justifiable answers to the following concerns. What is your or your customer's expectation of the product service you sell or that your customer buys? That is, what is a good estimate for the mean value? Companies want to sell something, they want more customers. You do a customer survey. You want them to answer questions that are going to help the company sell more. And given the information about your customer's average expectation, what is a good quality of the product you sell? That is, what is a good estimate of the deviation from the mean? And sorry about that in front of a question mark. I guess it didn't take that symbol. There's a symbol S and S squared, or sorry, S squared is the variance, and the square root of that is called the standard deviation. How much does it vary away from the middle of your data? And given the information about your customer's expectation and the quality of the product you sell, how does your product service compare with other existing products or services offered by your competitors? And that is, you are comparing different means. And as I previously had said, that is really what you are doing in statistics. You're measuring the means, and you want to, is there a statistical difference? So if you have a company or you're working for a company and they're going to have, and they have competitors, you want to find out what is it that they do that makes them better, or what is it that you do that makes your company better? And that is by testing and evaluating the means of whatever the product is that you're measuring. So the two main branches of statistics are descriptive statistics and inferential statistics. Descriptive statistics deals with the presentation and collection of data, and this is usually the first part of a statistical analysis. Would you like me to try to get the video on, or do you want me to try to explain it to you? Try for the video? Okay. All right, just give me a couple of minutes and let me try to get this. Okay, hopefully we can get this quickly. All right.
Imagine that you are interested in measuring the level of anxiety of college students during finals week in one of your courses. You have 11 study participants rate their level of anxiety on a scale from 1 to 10, with 1 being no anxiety and 10 being extremely anxious. You collect the ratings and review them. The ratings are 8, 4, 9, 3, 5, 8, 6, 6, 7, 8, and 10. Your teacher asks you for a summary of your findings. How do you summarize this data? One way we could do this is by using descriptive statistics. Descriptive statistics are used to describe or summarize data in ways that are meaningful and useful. For example, it would not be useful to know that all of the participants in our example wore blue shoes. However, it would be useful to know how spread out their anxiety ratings were. Descriptive statistics is at the heart of all quantitative analysis. So, how do we describe data? There are 2 ways: measures of central tendency and measures of variability or dispersion. You are probably somewhat familiar with the mean, but did you know that it is a measure of central tendency? Measures of central tendency use a single value to describe the center of a data set. The mean, median, and mode are all the 3 measures of central tendency. The mean or average is calculated by finding the sum of the study data and dividing it by the total number of data. The mode is the number that appears most frequently in the set of data. The median is a middle value in a set of data. It is calculated by first listing the data in numerical order, then locating the value in the middle of the list. When working with an odd set of data, the median is the middle number. For example, the median in a set of 9 data is the number in the 5th place. When working with an even set of data, you find the average of the 2 middle numbers. For example, in a data set of 10, you would find the average of the numbers in the 5th and 6th places. The mean and median can only be used with numerical data. The mode can be used with both numerical and nominal data, or data in the form of names or labels. Eye color, gender, and hair color are all examples of nominal data. The mean is the preferred measure of central tendency since it considers all of the numbers in a data set.
Okay. Oh, sorry. So any questions about descriptive data or descriptive statistics? Everybody understand that? Okay, I'm going to try to show the video on inferential statistics.
With inferential statistics, we generally take a sample, or a small subset of a larger set of data, and we use this sample to draw inferences about the population as a whole. Let's consider some examples. You have been hired by the National Election Commission to examine how the American people feel the fairness of the voting procedures in the US. How will you do it? Who will you ask? It would be virtually impossible to ask every single American how he or she feels about the fairness of the voting procedures. Rather than ask every American then, you could sample the population and then draw inferences about the entire population based on the sample. A sample is a smaller subset of the population. In taking a sample, consider how important it is for us to get an unbiased sample. For instance, what happens if all of your sample happens to be composed of Florida residents? Alternatively, what happens if the sample you choose is composed only of Republicans? Since inferential statistics are based on the assumption that sampling is random, your sample would not provide a valid basis for generalizing to the population. As you might imagine, it is very easy for a sample to be biased. Thus, there are strategies that researchers adopt in an attempt to eliminate or decrease the bias in their sample. One of these strategies is the use of simple random sampling. Simple random sampling occurs when every member of the population has an equal chance of being selected into the sample. In addition, the selection of one member is independent from the selection of another member. In theory, then, the strategy of simple random sampling involves selection into a sample by pure chance. To see why random sampling is important, consider the following ways that a sample can be obtained. To build on your understanding of sample and population, identify both of these, and then consider the problem or problems with how the sample was selected. In this example, a substitute teacher wants to know how students in the class did on their last test. She asks only the 10 students sitting in the front row to report how they did, and concludes that the class did extremely well. What is the sample? What is the population? Can you identify any problems with choosing the sample in the way that the teacher did? The sample is the 10 students sitting in the front row. The population is all students in the class. The problem with choosing this sample is that it is biased. Those who sit in the front row of classes tend to be more interested in the class and tend to perform higher in the class than the students who sit in other places in the classroom. Thus, the sample may be performing much better than the population. If the substitute teacher puts every student's name in a hat and randomly chooses 10 names out of the hat, the sample would not be biased. Consider another example. In this example, a coach is interested in seeing how many cartwheels the average college freshman at his university can do. The coach chooses 8 volunteers, all of whom happen to be women, and concludes that college freshmen can do an average of 16 cartwheels in a row without stopping. What is the sample? What is the population? Can you identify any problems with choosing the sample in the way that the coach did? The sample includes the female students who volunteered to do cartwheels. The population includes all freshmen at the university where the study was conducted. The problem with choosing the sample is that, again, sampling was not used, and so generalizations back to the population can be grossly inaccurate. Rather than randomly sample from all college freshmen and ask them to turn cartwheels, the coach chose only women and chose only those who volunteered. First, we might assume that women generally outperform men in turning cartwheels. More women are in gymnastics. Cartwheels tend to be an activity that little girls pursue more than boys. And so the number 16 would be biased. Second, those that volunteer to do cartwheels can probably do cartwheels very well. In other words, a person who can't do cartwheels probably would not volunteer to do them. Thus, the sample may be missing individuals who suffer in cartwheel abilities, and hence, the sample inflates the number relative to the population. Sometimes it is simply not possible or feasible to take a simple random sampling. For instance, consider that both Dallas and Houston were vying to be hosts of the 2012 Olympics, and assume you were hired to assess whether Texans, as a whole, would prefer the Olympics to be in Dallas or Houston. Because you have already learned the difficulty of getting every single Texan's opinion, you know you must get a sample, and you want to use simple random sampling. However, even this may be very difficult. For instance, how will you get a hold of those individuals who don't vote, who don't have phones, and whose addresses have changed? What do you do with those individuals in the sample who happen to move from Texas to California? What do you do about the fact that since the beginning of the study, an additional 4,212 people moved to the state of Texas? As you can see, it is sometimes very difficult to develop a truly random procedure. Recall that the definition of a random sample is a sample in which every member of the population has an equal chance of being selected. This means that the sampling procedure, rather than the results of the sampling procedure, defines what it means for a sample to be random. Random samples, especially if the sample size is small, are not necessarily even roughly representative of the population. For example, if a random sample of 12 were taken from a population with an equal number of males and females, there would be approximately a 1 in 5 chance that 2/3 or more of the sample would be female. Such a sample would not be representative, although it would be random. In short, only with a large sample size will a random sample ensure an approximately representative sample.
Okay, was that understandable? Yeah, does everybody understand that? Differences? Good. Any questions about that? No? Yes? Trishit? You have a question? Oh, sorry. Okay. So what I want you to do from that video, and remember, all the PowerPoints are online so you can download them and watch them as often as you want, is to think about, if you're not going to use any of the data from the data files that are in the course website and you want to collect your own data, remember the examples. You do not want to make your sample biased, which means your sample size might be too small. We're going to talk about sample size, not for a while, but the recommended sample size is an N, which is basically the sample size, of 30 to be representative of the population. And remember, you have to come to me and tell me, if you're not going to use the existing data that's in the course website and you're going to pick your own data, you have to tell me what the data is, where you're getting it from, and what is it that you want to measure. Okay? So just to summarize, inferential descriptive statistics deals with the presentation and collection of the data. Usually the first part of a statistical analysis, you're describing the mean, the mode, the median, the variance, the standard deviation, how much it varies from the mean. And inferential statistics involves drawing a conclusion from the statistical analysis that has been performed using descriptive statistics. And most predictions about the future and generalizations about a population by studying a smaller sample come under the purview of inferential statistics. And both descriptive and inferential statistics go hand in hand, and one cannot exist without the other. Good scientific methodology needs to be followed in both of these steps of statistical analysis, and both these branches of statistics are equally important. One is not more important than the other. So we then have a population versus a sample. The population, as I explained earlier, is the whole. It's the collection of persons, objects, or items under the study. So you want to study a particular bird. Say you want to study sparrows, a particular species of sparrows. That is the whole population of that you want to study. The census is the method of gathering the data from the entire population. And the sample is a portion of the whole, and it's a subset of that population. Any question about these three terms? No questions? Okay. All right, good. Okay, so for example, this, excuse the drawing, this is a population of these particular cars. I'm not sure whether they're supposed to be some kind of special car, whatever. That is the population. And in this population, there's 12 cars. Okay, and this is some of the descriptive data. On the left side under identifier, and when you collect data, usually identifier is whatever number it is, it's a random number, but usually it starts with 1 and goes up, and it doesn't matter which person, object, or information it is. It's just an identifier that's for you as the researcher, it's not for anybody else. And they decided to look at the colors. And in this case, we have red, blue, green, and gray. So we have 4 different colors. And they also look at what are the miles per gallon. You can tell it's American, I apologize. Anyways, you can also look at and eventually do some analysis. We can look at like, what are the red color cars average MPG, you know, as opposed to the blue ones, as opposed to the green ones, as opposed to the gray ones. However, does someone see a problem with doing an analysis of this? No problems? Anybody see a problem? Okay, it's sort of a trick question. Because you only have 12 as the total population, that's a very small population. But if it is the population, you can do an analysis on it. Remember what has been said in the videos and what I've said. Usually you don't have a population of whatever you're measuring as low as a number 12. Usually, you know, it can be the hundreds and thousands, millions, whatever. You usually only have access to a sample. Here you have access to a population, so you can actually determine, you know, do red cars have a better MPG than green cars? And you'll notice there's only 2 green cars. That size is really small. And I'll just tell you right now, when you have a grouping such as color in this case, the number of items within that grouping also matters when you do analysis. And usually, this is usually, and depends on, you know, what are you measuring. If anything is less than 10, and say you get a statistically significant result, you have to be very wary, just because the sample, not the sample, the actual population size is tiny. Okay, so remember that if you're going to collect your own data. So following it up, they took a sample. They took 2 red cars, a green car, and a gray car. But because the size is so tiny, it can lead to problems, right? Because you could say, oh, you know what? The green car gets the better MPGs than the other groups. Well, you only have a sample of 1. So you also have to watch that as well. Okay, a parameter versus a statistic. I'm going to show you the video for this. If I can get to it. Oh my God, okay. Sorry, everybody. And why isn't this going? Sorry, my machine is, well, the connection is very slow. Anybody have any questions? No, this is not in the, well, the elements are there. The exact examples that I'm giving in the PowerPoint are not there because I made them up or got them from another source. But in the study guide, it'll be exactly the same.
This is Stephanie from statisticshowto.com, and I'm going to be
Sorry,
explaining this video tutorial
just,
the difference
oh my
between
God.
a statistic and a parameter. A statistic and a parameter are very similar. They're both descriptions of groups. For example, 50% of cat owners prefer X brand cat food.
Sorry.
That could be a statistic and it could be a parameter. A statistic is a fraction of the population. That's what we call a sample. And a parameter. This is Stephanie.
Okay, sorry about that. Okay.
From statisticshowto.com, and I'm going to be explaining in this video tutorial the difference between a statistic and a parameter. A statistic and a parameter are very similar. They're both descriptions of groups. For example, 50% of cat owners prefer X brand cat food. That could be a statistic and it could be a parameter. A statistic is a fraction of the population. That's what we call a sample. And a parameter is the whole population.
Okay, so it's just using different words. The statistic is the fraction of the population, referred to as the sample, and the parameter is the whole population. So if you see those words, you know parameter equals whole population and statistic equals sample.
There's a couple of steps you can take to determine whether you've got a statistic or a parameter. The first question you can ask yourself is this obviously a fact about the whole population? Sometimes it's pretty easy to figure out. For example, with small populations, you usually have a parameter because the groups are small enough to survey, either for logistical or financial reasons. You don't really want to survey millions of people, but if you've got a small group, you can be pretty sure that you have a parameter. Here's a few examples of parameters. 20% of US senators voted for a particular measure. Well, there are 100 senators in the Senate, so you can be pretty sure that all of them were counted in this vote. So you have a parameter. Another parameter, 10% of 2,033 students at a particular elementary school got an A on a standardized test. Well, you've got the figure right there, 2,033 students. So you're being told that all of them were surveyed. Another example of a parameter, 33% of 520 workers at a particular car factory were paid more than $50,000 a year. Well, again, you've got a population there, 520. So this is a set of facts about the whole population. So we have parameters. These three examples here are all statistics. 50% of US residents support universal health care. The current US population is 311.6 million people. You're not going to want to survey 311.6 million people for anything other than the US Census. So you can be sure that 50% of US residents on any fact at all is most likely going to be a statistic, with the exception of any data that comes out of the US Census. Another example here of a statistic, 35% of Jacksonville, Florida residents have visited the state fair at least once. The population of Jacksonville is about 800,000 people, so this takes a little logic. You can bet that someone surveying people to find out if they visited the state fair isn't going to want to expend the kind of money you need to survey 800,000 people. So this is a statistic. Final example of a statistic, 30% of cat owners have an outdoor cat. There are several million people in the US that own a cat, so anybody surveying anything about cats, again, isn't going to want to spend that kind of money. That's the difference between a statistic and a parameter. This is Stephanie from statisticshowto.com. Visit us for more articles and videos on elementary statistics.
Okay, so is it clear what the difference is between a statistic and a parameter? No, Ocean? What's the problem?
Oh, that was a response to something before.
Oh, that was from the quiz guide you were
Yeah.
Oh, okay. I thought that was pretty clear anyway.
Yes, it was clear.
Okay, all right. Yeah, so it basically is just the different terms. It's like nothing more complicated than that. Okay. All right. I don't know how familiar people are, and I don't know how much statistics you did in your math course, but we'll just go over this. The first symbol looks like a U with a little squiggly on the left side. That's referred to as mu. You know, when a cat mews or meows, it's mu, and that denotes population parameter or the mean. The second one is the symbol that looks like a 0 with a curly Q, and it's squared. That's called sigma, and that is the population variance. So how much, whatever you're measuring, how much does it vary from the mean? And when you take the square root of the variance, you get the population standard deviation, which is just sigma. And usually in statistics, people don't really use the variance that much. They use it basically to figure out what the population standard deviation is, because that is what you're measuring against. Have people done, have people looked at what's referred to as Z-scores? Has anybody done that in their previous math classes? Yes, you have. Oh, okay. Not fully. What does that mean? What does that mean?
I read, like, I just kind of skimmed over it, but I don't fully understand it.
Oh, okay.
Sorry.
Basically, what you're doing is, I'll deviate a little bit, but has everybody studied, I guess, what's referred to as a normal curve? Like it looks like a bell. That's a normal distribution.
Oh, yes.
Okay. In a normal distribution, you have these divisions of standard deviations, and that is the best way to see whether you have two groups and you're doing an analysis and you want to see what's the difference between this group and the other group, and then you look at what their averages are. And usually, we'll get into this, if something is above or below one standard deviation from the mean, you know that that number is statistically significant because the mean is based 68% of the population. Okay? And the other 32% are on either side of the curve, and they're divided into what's referred to as the 95th percentile and the 99th percentile. We will talk about those things, but the standard deviation is usually the easiest way to denote statistical significance. Then you know it's outside of what 68% of the population is. And usually if anything is outside that 68%, it means statistical significance.
Okay, I get it. It's from finance. I understand the standard deviation and stuff like that.
Yeah.
Okay.
All right. Okay. And the X denotes the sample mean. Sorry, X bar, the little bar above the X. If it's a big X, that's a population mean. And the S squared denotes the sample variance. And the S denotes the sample standard deviation, basically just taking the square root of the variance. So this is the process for inferential statistics. You calculate the mean to estimate the population mean. Population mean is the parameter, the sample mean is the statistic, and then you select a random sample. So there are different levels of data measurement. And I assume did everybody cover this? The levels of measurement? Does this look familiar? Nominal, ordinal, interval, ratio? Okay, for those that haven't, the nominal level of measurement is you're measuring using a nominal scale. One simply names or categorizes responses. Gender, handedness, you're left-handed or right-handed, your favorite color, religion. There are examples of variables measured on a nominal scale. One, why it's nominal is you're just labeling it. Somebody has brown eyes, somebody has blue. One is not better than the other. One is not higher than the other. Okay, they're just labels. So when you have nominal data, or what's referred to as frequency data, you're just measuring, you're just counting. How many people in the class have blue eyes? How many people in the class have brown eyes? How many people in the class have bloodshot eyes? Whatever. Okay, you're just measuring some kind of measure of a variable that you're looking at. How many people have brown hair? How many people have red hair? How many people have dyed hair? You know, the essential point about nominal scales is that they do not imply any ordering among the responses. As I said, one is not better than the other. So for example, when classifying people according to their favorite color, there's no sense in which green is placed ahead of blue. Responses are merely categorized. Nominal scales embody the lowest level of measurement, and usually it's referred to as categorical data. Okay, but you can do analysis on that, and you can get statistically significant results. Do you want to see the video on the levels of data? Just, tell me whether you want to or you don't. Yes, okay. Samar, yeah, okay. All right. Let me get that one up. Okay. Sorry, I have to go through this nonsense of sharing the screen and sharing the application. Well, I hope it's not too irritating.
In this video, we'll take a look at what are known as the scales of measurement. Okay, first of all, measurement can be defined as the process of applying numbers to objects according to a set of rules. Now, at first, this definition may look a bit daunting, but let's go ahead and break it down, and I think you'll see that it's really not that bad. So, when we measure something, we apply numbers or we give numbers to something, and this something is just generically an object or objects. So we're assigning numbers to something or things, and when we do that, we follow some sort of rules. Okay, so for example, we all are actually very familiar with measurement. If we measure someone's height, we might have them stand against a wall, and then we take a tape measure and we extend it vertically until it meets the top of their head. And we read off on that ruler how many feet and how many inches they are. So we might read out 5 feet 9 inches, and that indicates their height. So we applied numbers to an object, in this case a person, according to a set of rules. And the rules is you extend the tape measure from the ground vertically up until it reaches the top of their head, where we're level there at the top of the head, and we read off how tall they are. So that's measurement. Now, in terms of introductory statistics textbooks, there are 4 scales of measurement: nominal, ordinal, interval, and ratio. We'll take a look at each of these in turn and take a look at some examples as well, as the examples really help to differentiate between these 4 scales. First, we'll take a look at nominal. Now, in a nominal scale of measurement, we assign numbers to objects where the different numbers indicate different objects. The numbers have no real meaning other than differentiating between objects. So as an example, a very common variable in statistical analyses is gender, where in this example, all males get a 1 and all females get a 2. Now, the reason why this is nominal is because we could have just as easily assigned females a 1 and males a 2. Or we could have assigned females 500 and males 650. It doesn't matter what number we come up with, as long as all males get the same number, 1 in this example, and all females get the same number, 2. It doesn't mean that because females have a higher number that they're better than males, or males are worse than females, or vice versa, or anything like that. All it does is it differentiates between our 2 groups. And that's a classic nominal example. Another one is baseball uniform numbers. Now, the number that a player has on their uniform in baseball, it provides no insight into the player's position or anything like that. It just simply differentiates between players. So if someone has the number 23 on their back and someone has the number 25, it doesn't mean that the person who has 25 is better, has a higher average, hits more home runs, or anything like that. It just means they're not the same player as number 23. So in this example, it's nominal, once again, because the number just simply differentiates between objects. Now, just as a side note, in all sports, it's not the same. Like in football, for example, different sequences of numbers typically go towards different positions. Like linebackers will have numbers that are different than quarterbacks and so forth. But that's not the case in baseball. So in baseball, whatever the number is, it provides typically no insight into what position they play. Okay, next we have ordinal. And for ordinal, we assign numbers to objects just like nominal. But here the numbers also have meaningful order. So for example, the place someone finishes in a race, first, second, third, and so on. If we know the place that they finished, we know how they did relative to others. So for example, the first place person did better than second, second did better than third, and so on, of course, right? That's obvious. But that number that they're assigned, 1, 2, or 3, indicates how they finished in a race. So it indicates order. And the same thing with the place finished in an election, first, second, third, fourth. We know exactly how they did in relation to the others. The person who finished in third place did better than someone who finished in fifth, let's say, if there are that many people. First did better than third, and so on. So the number for ordinal, once again, indicates placement or order. So we can rank people with ordinal data.
I just want to stop there because I want to also show you, if we look at the example 1, the place somebody or people finished in a race, first, second, third, and so on. It's also not just the order, this is what makes it ordinal, but also you can say, well, if it was a running race, you can say, well, the first place person ran faster than everybody else in the race. And the second ran faster than everybody else in the race except for the first person. So I want you to look at the data like that. When you have ordinal data, you can also do different evaluation of that data. The same with the election. The first place person got the most votes. The second place person got the most votes except for the first place person. So look at the data like that because it's really important, because that's how you capture information from data that you wouldn't think had that kind of information, but that's looking at the data in that way.
Okay, next we have interval. In interval, numbers have order, just like ordinal. So you can see here how these scales of measurement build on one another. But in addition to ordinal, interval also has equal intervals between adjacent categories. And I'll show you what I mean here with an example. So if we take temperature in degrees Fahrenheit, the difference between 78 degrees and 79 degrees, or that 1 degree difference, is the same as the difference between 45 degrees and 46 degrees. 1 degree difference once again. So anywhere along that scale, up and down the Fahrenheit scale, that 1 degree difference means the same thing all up and down that scale. Okay, so if we take 8 degrees versus 9 degrees, the difference there is 1 degree once again. That's a classic interval scale right there, where those differences are meaningful. And we'll contrast this with ordinal in just a few moments. But finally, before we do, let's take a look at ratio.
Oh, and sorry, that was the end of that. So does this remind people of anything? Did you talk about this? The measurement of data? Okay, so here are some common types of variables. Categorical variables. We talked about variables that can be put into categories. For example, the category toothpaste brands, which might contain the variable Colgate and Aquafresh or Crest. Now, hopefully you will not come across this if you decide to do your own data, but a confounding variable, which is an extra variable that has a hidden effect on your experimental results. A confounding variable is also referred to as noise. So when somebody sets up an experiment or they're doing some research and they're trying to control the experiment, something may cause a problem with the results that you have. And so it's very important when collecting data that you check out for confounding variables or noise. A continuous variable is a variable with an infinite number of values like time or weight. A control variable is a factor in an experiment which must be held constant. For example, in an experiment to determine whether light makes plants grow, you would have to control for soil quality and water. A dependent variable is the outcome of the experiment. As you change the independent variable, you watch what happens to the dependent variable. A discrete variable is a variable that can only take on a certain number of values. For example, the number of cars in a parking lot is discrete because a car park can only hold so many cars. If you were very interested in finding out about parking in the city of Toronto, you might want to check all the parking lots. Not very exciting, but you know, it is data. An independent variable is a variable that is not affected by anything that you, the researcher, does. Usually is plotted on the x-axis. Okay? So, if you're measuring the difference between males and females, you cannot change the males and females. They're males or females. Nominal variable, another name for categorical. Ordinal, similar to categorical, but there's a clear order. We looked at that. A qualitative variable is a broad category for any variable that can't be counted. For example, has no numerical value. Nominal and ordinal variables fall under this umbrella term. And I will explain to you that when you have qualitative variables and quantitative variables, there are different applications that you can use to evaluate those variables. And as I sent you a note out regarding the research, then when you know whether your data is qualitative or quantitative, you know what kind of analysis you're going to do. A random variable are associated with random processes and give numbers to outcomes of random events. A ranked variable is an ordinal variable, a variable where every data point can be put in order. So it can be first, second, or third, which we discussed in the example. A ratio variable is similar to the interval variables, but has a full zero. Zero means something in this measurement. The less common types of variables are active variables, a variable that is manipulated by the researcher. You're not going to do that in this particular case. Perhaps when you've graduated and wherever you work, you may actually be involved in something like that, where you are in control and you're manipulating a variable. Attribute variables, another name for categorical variable. Binary variables are variables that can take on only two values, usually 0 or 1. It could also be yes or no, tall or short, or some other two variable combination. Collider variables are variables represented by a node on a causal graph that has paths pointing in as well as out. Variate are similar to an independent variable and it has an effect on the dependent variable, but is usually not the variable of interest. A criterion variable, another name for a dependent variable. You'll see some of these names are mixed with each other and they have the same meaning, but you may see a different label, and so you should understand which ones are similar. A dichotomous variable is another name for a binary variable. Some of you may have heard of dummy variables, which are used in regression analysis. And I don't think we're going to do regression analysis unless you, some of you, if anybody's interested, are going to take 2011, which is where we talk about regression analysis. For example, had the categories has dogs and owns a car, you might assign a 1 to mean has dogs and 0 to mean owns a car. Endogenous variables, similar to dependent variables that are affected by other variables in the system. It's used almost exclusively in econometrics. Have you learned this term? Anybody taken economics? I assume everybody. Did you learn this term, endogenous variable? Anybody there? Everybody asleep? Okay. You forget. Okay. Why didn't you say you were asleep? Okay. No. Okay. You didn't go that far in econometrics. Okay. Exogenous variables are ones that affect others in the system, can be like similar to noise. Explanatory variables are a type of independent variable. When a variable is independent, it's not affected at all by any other variables. When a variable isn't independent for certain, it's an explanatory variable. Extraneous variables are any variables that you are not intentionally studying in your experiment or test. Other words, it's noise. You don't want noise when you're doing an experiment. A grouping variable is also called a coding variable. A group variable or bivariable sorts data within data files into categories and groups. So you're going to say, oh, I'm going to check the heights of people. So I'm going to have all the males under 5'5". I'm going to have all the females, and you give them a label, and that's all it is a label. You can compare the groups, but you don't do an analysis within that. Well, you can do it within the group, but you're not analyzing the group label. And let's see, okay. Just one more. I just want to go back because this is, and a nuisance variable is an extraneous variable that increases variability overall. An observed variable, sometimes called observable variables or measured variables, are actually measured by the researcher. If you're working with a structural equation model, they are data that actually exist in your data files, data that has been measured and recorded. They can be discrete or they can be continuous. Discrete, remember, it's not on a continuous scale, and a continuous scale is like the temperature outside. It can go up, it can go down. Outcome variable is similar in meaning to a dependent variable. A polycotomous variable can have more than two values. That variable can be ordered, unordered, or sequential. You don't want variables like that. If they take on more than one value, it makes your analysis very complicated. The predictor variable is similar in meaning to the independent variable, but used in the regression and non-experimental studies. A responding variable, which is an informal term for dependent variable. The scale variable is basically another name for a measurement variable, and test variable is another name for the dependent variable. Okay, so we looked at that, the nominal, the ordinal. In the ordinal measurement, the distances between attributes do not have any meaning. So for example, on a survey, you might code educational attainment as 0. I'm sure most of you, if not all of you, participated in some kind of survey. 0 equals less than high school, 1 equals some high school, 2 equals high school, 3 equals some college, 4 equals college degree, 5 is post-college. Okay? So that looks familiar. In this measure, higher numbers mean more education. But is the distance from 0 to 1 the same as 3 to 4? Of course not. Okay? There's a difference between some people who take courses at college and other people who graduate from college. So the interval between the values is not interpretable in an ordinal measure. And again, I'll go back to when you're going to do your assignment. Very important, and you can look at that sheet that I posted. You must determine what kind of data you have from the beginning, because otherwise you would probably do the incorrect analysis and come up with the incorrect conclusion. So that's very important to identify the types of variables that you're using. In interval measurement, the distance between attributes does have a meaning. So for example, when you measure the temperature in Fahrenheit or centigrade or Celsius, whatever you want, the distance from 30 to 40 is the same as the distance from 70 to 80. Or in Celsius, from 0 to 10 is the same as from 10 to 20. The interval between values is interpretable. Because of this, it makes sense to compute an average of an interval variable where it doesn't make sense to do so for ordinal variables. But you must note that the interval measurement ratios don't make any sense. So say we looked at Celsius. Is 20 twice as warm as 10? Is 20 centigrade twice as warm as 10 degrees centigrade or Celsius? Anybody?
Yes.
It is? 20 is twice as warm as 10?
Twice as warm, I believe so.
You do? Okay. Okay. If you convert 20 to Fahrenheit, it comes out to 68. If you convert 10 to Fahrenheit, it comes out to 50. Is 68 twice as much as 50?
No.
No. So in the world that you live in, you don't want it. You don't want it hotter than, like, I don't know what, 30, 25?
Oh, 18.
18. Okay. You don't even want room temperature, which is 20. Okay.
Is that normal? I do 18.
18. Okay. But
All year round.
do you see that it's not twice as warm?
Yeah, I
No,
get
you
that. No, I do. I
Okay.
do. But I did not know the conversion difference. And
Well,
yeah.
I mean, it's the same because it's an interval. The temperature measurement is interval. Okay. The measurement in between is the same, but it's not twice as hot.
Okay.
Like, for example, in temperatures. Okay. So if somebody was, how tall are you in metric? Do you know?
5'5".
No, that's not metric.
Oh,
That's imperial.
160 something. What do you mean?
Are you taller than 1 meter?
Yes.
Okay. All right. Do you know how many centimeters you are?
Oh, since it says that I'm 165, I think, or 170.
Okay.
Yeah.
You're 170. Okay. So I'm 181. All right. So am I like 1.1 meters taller than you? Not, because if you multiply 70 times 1 point whatever to get to my height, is it going to come out the same? 1 meter is 39 inches. So that means I'm minimum 39 inches taller than you, which is impossible.
Right.
Okay. So I want you to notice a difference, and everybody notice a difference when you have interval data. You cannot make those assumptions about the data. All right.
Okay.
When we talk about the next one, when we talk about ratio data, that's where you can make those differences. Okay. There's always what's referred to as an absolute zero in ratio data. This means that you can construct a meaningful fraction or ratio with a ratio variable. So weight is a ratio variable. Okay, theoretically, and I don't want to get into nitpicking about this, somebody could weigh 0, theoretically, all right? And somebody could weigh infinity. We don't know. I'm saying theoretically, okay? So in applied social research, most count variables are ratio. So for example, the number of clients in the past 6 months. And why? Because you're going to have a 0 clients, right? And because it is meaningful to say that we had twice as many clients in the past 6 months as we did in the previous 6 months. Is that understandable? Because people get mixed up between ratio and interval, not usually between ordinal and nominal. So is everybody clear with the difference between ratio and interval? Yes? Okay. Anybody not clear about that? And most data that you will look at, or most data that you will be exposed to, will be usually ratio. Unless, of course, you're doing a survey and you're getting people's opinions, that's neither ratio nor interval, okay? That's ordinal or nominal. Okay, so here's some of the important aspects of data measurement. It's important to recognize that there is a hierarchy implied in the level of measurement, that the complexity of your measurement is going up from nominal. Remember, nominal is just naming. You're just saying, oh, you have green eyes or you have blue eyes. There's no value that is a characteristic, right? So green eyes don't mean something different than blue eyes. It's just the color, and it's just a category. So you have to be clear about that. You cannot assign a measurement to a nominal or ordinal value. So at lower levels of measurement, assumptions tend to be less restrictive, and data analysis tends to be less sensitive, which means when you analyze nominal or ordinal data, you can only go so far. You can't, if you do say a frequency, and say you look at every student that goes to George Brown, and you say, okay, I'm going to look at the color of hair of everybody that goes to George Brown. What's the best thing that you could say about the hair color of all the students at George Brown? Like, you could do the analysis in your head right now. So what could you say? Anybody? No? And don't throw in bald people.
Maybe the frequency you use,
The frequency, yes, you could say, okay, more people, okay, there's a higher percentage of people or a higher percentage of students that attend George Brown have brown hair, okay? And maybe the number is like, I don't know, 68%, okay? But what can you tell about those people anything else? Can you say they're smarter? They're not as smart?
No.
No, no, and that's really, really important, because when you are at the lower levels of data measurement, such as, you know, hair color, that's basically all you can say. And you cannot make an inference. And you can say, well, you know, George Brown attracts brown-haired people. So what? Does that mean anything? No. And, you know, you're taking a measurement, and you got to think about, well, what's important about that analysis? Is there anything important about it? Yeah, now you have a count. That's all you can say. So does everybody get that? Does everybody understand when you are evaluating the lower levels, like nominal and ordinal, you can only do so much when you're evaluating the data. You can evaluate it to a point. And then in your paper, you can say, yes, more brown-haired people attend George Brown College. Okay. And for that, okay, you might get 1 out of 10. I don't know, 1 out of 20. Anyways, so that's understandable. So at each level up the hierarchy, the current level includes all of the qualities of the one below it and adds something new. So you can see that it builds up. And in general, it's desirable to have a higher level of measurement, example, interval, or ratio, rather than a lower one, nominal or ordinal, because then you can do more analysis or evaluation of that particular data. Then you can make some meaningful conclusions if you find statistical significance. We will talk about statistical significance. So I want to make sure, is everybody clear about what the different levels of data measurement is? Is there any confusion? Clear, okay, for those that are still awake. Okay. So at the nominal level, numbers are used to classify or categorize. So for example, employment classification. 1 for educator, 2 for construction worker, 3 for manufacturing worker. It has nothing to do with 1 is better than 2 and 2 is better than 3. I want you to remember that. That becomes very important. When you are doing classifications, you are not measuring differences based on anything. Okay, it's just a label. And for example, ethnicity, 1 for African American, sorry, this is American, 2 for Anglo-American, 3 for Hispanic American. Again, it's just a label. It means nothing. It's just a way to categorize. And as noted, we are looking at frequencies here. We are not looking at continuous numbers. We are not looking at anything like that. Okay, so just to be clear. At the ordinal level, numbers are used to indicate rank or order. So the relative magnitude of numbers is meaningful. This is where meaning comes into play for the numbers that you are associating. So the differences between the numbers are not comparable. So an example would be ranking the productivity of employees. So we all work at a factory. We're all producing something. Okay, so Wellington makes, 300 iPods. Amanjot makes 277. Larry makes 12. Okay? Okay, so now what's the ranking productivity of the employees? Can anybody tell me? No one? Okay. Okay, Wellington makes 300. Amanjot makes 270 and Larry makes 12. What can you say about that? I know it's like sort of out of context, but just for the making the point about ordinal level measurements. Can anybody say anything? Well, what's Larry's productivity? Yeah, whoever made 300 made the most. What else? Wellington better. Yes, you can say that. And what is that 12? Oh, and 12? What does that mean, Ocean?
Sorry,
Yeah,
I thought that you said the last person made 12.
yeah, I did. But you wrote down 12. What does that mean?
Oh,
Can you say anything about the productivity of that person?
Yes, like per person, that's the estimate on how much workload per employee.
Sort of, but not quite. And it's Larry. It's not that person. Larry made 12 iPods.
Okay.
Okay. So yes, Wellington. Yes, that was the lowest number. Okay. What else does it mean? What can you take out of that number? He's terrible. Larry Wellington. Yes, Larry is the least productive. Okay. So you see already we went from nominal to ordinal. Now you can make some inferences. If I'm looking at the productivity of employees, and then you have like a whole list, and somebody's at the bottom and somebody's at the top because whatever they're producing, you've got a number there, right? What are you going to do with the person that's at the bottom? As you pointed out, Wellington, Larry's the least productive. What can you do? Yeah, you can let them go. Oh, you're a mean boss. Okay. A guide for better? You mean like give them training? Yeah, talk to them to be more productive. Yes, exactly. So you can make some inferences from those numbers. And what are you going to do with the person at the top? What are you going to do with them? What can you do with them? A bonus, exactly. A bonus, yeah. And have a competition to make them do better. Exactly, Pui. Exactly. See, I want you to think that way, because it's like, it's not just the number, because now we are at the ordinal level. The number has some meaning, correct? We're looking at production level. 12 is way less than 300. 12, you could say, is relatively poor compared to the 300. Now you have some options about what can you do. You can fire them. You can like talk to them. You can give them training. So I want you to see what you can do with that. Okay. So I just want everybody to understand, when you have the ordinal level, you can then make some inferences about it, right? Give them a bonus, fire them, whatever. So I want you to see that those are the options available. There's more options as you go up different measurement levels. So a taste test ranking of 3 brands of soft drink. So you've got, you know, somebody likes, I don't know, Dr. Pepper. So you've got to test, remember, and it goes back to, we're going to talk about this sample size. The more you have in your sample, the better representative is of the population. And I will keep repeating this and say, when you have a sample of at least 30, that can give you a minimal understanding of what the population likes. Okay? So if we have that kind of ranking, what do you do with the people at the top? Or what can you say about the people at the top? Anything? Okay, what do you mean by leadership? This is a taste test. So you're testing soft drinks. More people like the first drink and fewer people like the last drink. So what is that saying about the drink? Anything? Yes, exactly. It will do better in sales. The first one tastes better. Exactly. Produce more of the first one, right, Olga? See, I want you to look at that. When you get results, is now you can start to make inferences. Does everybody understand that? Yes. Does any not understand this? Because now what you're saying is there's some relative meaningful numbers coming out. You know, what would happen if you did a taste test and say you tested 75 people and there was 3 different soft drinks and 25 people in each of the soft drink categories liked the drink. So it was 25, 25, 25. What does that mean? They're equal? They're all good or they're all bad? Do you know that they're all good? How do you know they're all good, Ocean? No, you don't know. They're all bad? No, they're not all bad. You have to justify how you get that. Basically, Amanjot is correct. They're equal. We don't know if they're all good. We don't know if they're all bad, but we do know they're all equal. So we know there's no one soft drink that's worse than the other, and there's no soft drink that's better than the other. Does everybody see that?
Yeah, that comes down to individual preference, though.
No, but remember, you as the researcher, you're looking at that final number.
Mm-hmm.
Yes, it's personal preference. However, if it ends up that everybody, it's equally split, that doesn't mean there's a personal preference for any one of them. Like the last example with the productivity of the employees. It's clear that the difference.
25 each. Okay, sorry. I
Okay,
thought
so you understand that?
Yeah.
So if the numbers are so close together, you could say, well, you can't say, you cannot say, oh, the drink is terrible. The drink is good. No. Basically, the drink is the same for everybody because they split the number of the frequency of people liking it or liking one over the other. You see what I'm saying? Yes, and Wellington, you're correct, but you have to increase the number to try no, not a better result, a more definitive result, okay? Because you're deciding on what's the rank. If they all rank the same, you increase the sample size, the chances are one may end up better than the other two, one may end up worse than the other two, but you don't know that until you increase the sample size. So is everybody clear about that? Yeah? Okay. And then you have the final example, the position within an organization. 1 is for president, 2 for vice president, 3. Okay, can someone tell me what the rankings mean? Do they mean anything, or is it just a label? Yeah, level of authority and job. So the way that the label has been designated, so what you're saying is the president has a higher level of authority?
Yeah.
Yeah, okay, it's right, Bisa. It's our hierarchy. Has the highest salary. Yes, you can make that.
And different job positions, like different job criteria. Yeah.
Right. So, right, Kavita, the ranking describes the productivity level, okay? Yeah. The president may be a person who has lots of contacts and they're going to get lots of business for that organization, right? The employee is the one that's doing the work at front line, and therefore, I mean, they're important as well. So in a way, it's sort of a mix. You know, sometimes the 5 doesn't mean anything. Sometimes the 5 means, oh, maybe it's a lower salary, maybe it's less responsibility. But what I'm trying for you to understand is you can extract more information from an ordinal level. Okay? Is that clear?
Yes.
Yeah. Okay. So I'm gonna stop here. I just want to. I sent out a note, as I said, about the case study, about doing the research. Yes, Ocean. You had a question?
Yes, it's about the case study. Are you going to be assigning us partners, or do we find our own?
No, you are going to decide if you want to use any of the samples that good segue. Anyways, if you're going to use any of the samples that I provided, if you don't want to use any of those samples, and everybody has to present me with a research proposal, because I want to know what the data is and what are you going to do with that data and how you're going to analyze that data. Okay. Yeah. So if you don't if you've got and I didn't mention the last time, I'll mention it today. If you've got a passion for anything in particular, and it doesn't have to be related to business, it's something you like, or something you feel very strongly about, if you can get valid data, and I have to look at the data, you can do your case study on that. Okay, you know, so
and to do with the partners though, like
no, you don't have. No. Sorry, I don't want to confuse anybody. You can do it with a partner, or you can do it by yourself.
Okay.
Okay.
Yep.
And I want you to follow either one of those guides, but I do want people to provide me with a copy of the research proposal, the templates, you know, in the folder for the case studies. And if you have any questions, ask me. If you want to use your own, or you want to find some other data that you're really interested in, just remember what I mentioned in the last class. The data has to be from a valid source. That's the number one thing. So it can come from a government, it can come from an educational institution, it can come from if you're going to get it from a news organization or a newspaper, I want that newspaper to have been in existence before there was the internet. Okay? Yeah, John, what do you mean by Google? I meant Wikipedia. I don't want any data from Wikipedia. There are relative and relevant sources on Wikipedia. You can go to those sources. Can several students work on the same topic? Yes. Okay. Okay, what do you mean by Google would have to be from a legitimate source? I don't know what that means.
I'm just trying to say, because John was asking about Google, using Google
Yeah.
to find the stats, I'm just saying it would have to
Oh,
be
no.
a legitimate source.
No, you can, no, but you use Google to go to a source, right?
Yes, yeah.
The source, it's the source that's important. Google is great. I mean, you go find a source.
Yeah, that's how you find almost everything. Yeah.
Yeah. And the other thing is, I don't know whether anybody is aware, there's a thing called Google Scholar. Have people heard of this?
Yes, it's good.
If you go to Google Scholar and you type in, you know, I want to use some data or something, or, you know, from some area, it will actually give you academic information. It will give you legitimate information.
Things that have already been done by other people.
Oh, yeah. Oh, yeah. No, it's like real, let's put it this way, research. Okay. So you have to find the data, and it has to be valid data. And as I said, you know, it comes from a government organization. It can be the city or municipal, it can be provincial, it can be federal. It doesn't matter. Okay. They're as we went back to the beginning of the class, those are reliable sources. You know. So I want to mention one other thing. If you looked on the Collaborate page, there's something for office hours. Now I set up office hours for Monday from 10 to 12 and Wednesday from 10 to 12. You don't have to go to those. If you do have questions, I will be online from 10 to 12 on Monday and Wednesday. If it gets to be too many people, what I'll do is I'll divide the class alphabetically. You know, half the class will have Mondays and the other half will have Wednesdays. Okay, any other questions? No questions? Okay, so we're going to continue with this on Tuesday. And I have a feeling that we may finish Tuesday, which means the test on chapter 1 would probably be from Wednesday to Friday. And as I mentioned, you have 3 days. Let me ask a quick question. Is there anybody that's not in North America? Is everybody in North America? Ocean, where are you? Oh, Ahmed, for now? Okay. Okay, that's fine. So remember, that's why I'm, the evaluations, you will have up to 3 days to complete. And so that should cover everybody. And as I mentioned, there's a time limit, usually 2 hours. And what will happen is if you are not finished after 2 hours, your evaluation is automatically submitted. Okay? Any questions about that? Okay. So everybody enjoy the weekend. It's supposed to rain on Sunday. Otherwise, you don't have homework. Do you want to make yourself some homework song? You didn't want to answer the question, eh, Song? You need some practice. Okay, well, try the practice from the MyLab. And as I said, You can send me questions or concerns, or you can use the office hours. And as I said, if there's too many people, I'll split up the class just so that everybody gets their responses answered. All right, so everybody have a good weekend and take care, and we'll see you on Tuesday. Okay.